Thanks for joining me. Today we're going to begin our second unit in our chemistry class. This unit is called Matter and Energy. This is really the beginnings of your understanding of chemistry. The first unit was to give us some background and have some materials in our brain that would maybe help us understand all of this a little bit better. So let's start with a view of the calendar, where we think this is going to be happening or going. So I think we'll be starting this unit on the 10th of September, and we'll introduce matter and energy, and then on the 11th we'll discuss the difference between temperature and heat, and then on the 14th we'll talk about density. There may be a density lab or some activity this day. That's at least what I'm temporarily thinking we're going to do, followed by states of matter, mixtures in compounds, and then allotropes and alloys, and then we have a separation of mixtures day. It appears as though there's a teacher's institute, so all this might get pushed back a day. Then we'll talk about energy, and then like kinetic and molecular energy, and then nuclear fission versus nuclear fusion, and then we'll have a review day, and then we'll probably take a test. After that, we'll have a little mini unit on calorimetry, and we'll spend maybe 5 days from the start to the time we take our assessment on calorimetry. So that's basically how I see the end of September going for us. So let's get right into the PowerPoint. So if we look at this, I don't know if that's the Big Bang going off, the beginning of the universe, right, where maybe there was a tremendous amount of energy released and matter was formed. And this unit is called Energy and Matter. If you look up the definition of chemistry, it's the study of matter and the energy changes it undergoes. So let's get started. So here's some questions. These aren't important questions, but they're the type of questions we could think about. Like, why is it that substances boil or freeze at different temperatures, right? Like, why does water have to get so cold before it actually freezes, and other things freeze at room temperature? They're solid at room temperature. So we'll talk about that, what causes differences in freezing points. Why do you put salt on the roads in the winter, right? It's clearly not to season the road because you're going to eat it. It's maybe something to do with it's going to melt the snow or ice that's on the road. But if you get to a really cold area, maybe Fargo, North Dakota, where it's 20 degrees below zero, they don't use salt because it won't work to melt the ice. Instead, they use sand on the roads to give a little bit of grit. So we'll talk about colligative properties and things such as that. We might talk about how the process of sweating will cool us, and if we become very dehydrated and we can no longer sweat, we might get heat stroke. So again, I'm trying to make these examples real life, relevant examples, not just have you memorize a bunch of facts. We'll talk about what is energy, the ability to do work. We'll talk about stored energy, potential energy, and energy of motion, kinetic energy, as well as fission and fusion, nuclear energy, and how those are generated. Then we'll talk about what units do we use to measure energy, calories or joules, and so on. So that is just a few questions we could think about, I suppose, as we approach this unit. So this is a table of contents talking about the different things that we will discuss within this unit. You probably don't need to bother yourself with that right now, but you can see there's actually quite a few topics that we will be talking about within this unit. So let's go ahead and get started. So if you were in class, I would have taken a box of matches, these strike anywhere matches, and I would have asked you to tell me how to light the match, and you'd say strike it on the box. And I, of course, would not strike it on the part you're supposed to, and it wouldn't work, and you'd tell me I'm stupid or something, and then you'd tell me do it on the side, and of course I would use the ends, not the side, with the proper material. And then you'd say use it on the side with the red stuff, and finally I would, but I would turn the match backwards, so I was rubbing the back of the match, making you very frustrated that I was unable to light the match, even though I point out that it says strike anywhere matches. So maybe that's a little not truth in advertisement. Now, there are strike anywhere matches and there are safety matches, and the ones that I would have been using would have been safety matches where it says strike on the box. So, but it's only on these ends, this red end and the other end, that it actually works. So what is the chemistry of that? And again, I will not ask you the chemistry of this. I'm simply making a bigger point. It starts with this material here, tetraphosphorus trisulfide. Now, we're not doing nomenclature or naming right now, but I think this might make some sense to you. Maybe you played Tetris. That was a game where 4 blocks would come down and you have to make them fill in the spaces, right? Tetra means 4. So there's 4 phosphorus, P4, and then I think of a tricycle has 3 wheels, 3 sulfurs, so tetraphosphorus trisulfide. And you're going to react that with some potassium chlorate. And the potassium chlorate is a second reactant. So the phosphorus is actually on the side of the box of matches. That's the tetraphosphorus trisulfide right here. And the potassium chlorate is on the tip of the match. And until those two make contact, that match will not go. So that's what makes it a safety match. A strike anywhere match has both ingredients on the match head. So if you simply rub it against an unshaven face or throw it against the concrete or simply open the drawer too abrupt with too much energy, you can cause those matches to ignite. The ones you have at home, I assume and hope, are strike on the box matches, not strike anywhere matches. Strike anywhere matches are fine if you're going camping. They generally need to be stored in a airtight metal container so that if they were to go off, because it's airtight, it will not burn very long because there won't be enough oxygen. I think you can remember what this little triangle means. It means change or fire, right? So we took these reactants and then they got rearranged and we ended up forming diphosphorus pentaoxide, potassium chloride, and sulfur dioxide. And the sulfur dioxide is the smell. If you like the smell of burning matches, that's what you're smelling, is sulfur dioxide. In higher concentrations, sulfur dioxide can be fatal, but if you light 1 or 2 matches, it's certainly not going to harm you in any way, shape, or form. All right, well, that's kind of showing you what happens. There was some stored or potential energy in the matches when they started, and then afterwards they gave off energy in the form of heat and light, and as well as gases in the rearrangement of atoms. So that's what was happening in this particular situation. All right, let's keep going. And again, I won't ask you any questions on a test or quiz about the chemistry of matches. This was simply to kind of give you a background of how these things can relate to this unit, matter and energy. All right, well, let's look at this box here. It's a block of wood. It has a length of 2 meters, a width given, and a height given. And if I were to set that on a counter, it would exert a certain force. And we'll define that force as 45 newtons. Force is a derived unit. It's a pressure divided by an area. And so let's look at this. Here's a definition of a newton. It's 2.205 pounds. That's equal to 10 newtons. It's really 9.8, but we'll call it 10 newtons or a kilogram. Now, what's the difference between force and pressure? Well, depending on if we were to lay the block of wood this way, it's going to have these dimensions. And so the area, the face that's touching the blue, has an area of 0.9 meters times 2 meters, or 1.8 meters squared. And I said pressure is a force divided by some area. The more force you apply to a small area, the more pressure you feel. Likewise, if you apply a force over a very large area, then you divide by a big number, you get a small pressure. Perhaps it'll be the middle of the winter and you'll be ice fishing. I'm not sure why you want to go ice fishing, but if you do, if you hear the ice crack under your feet, you should not start running. If you run, you're probably going to fall through the ice. Instead, you should lay out, put your arms and legs out, and get down to the ground and then sort of shimmy off there, because you're trying to put as little force on the ice as you can by applying the force of your body over not just the area of your feet, but over your entire surface of your body laying against the ice. So the pressure here, remember, it would be the force of 45 newtons that we started with divided by our area of 1.8 meters squared, comes out to be 25 newtons per meter squared. If I turn that block on its side, notice now there is less area pushing down. So now the area is only 0.5 meters times 2 meters, or 1 meter squared. The force is still the same, 45 newtons divided by our 1 meter squared. So the pressure on the block now is 45 newtons per meter squared. And if I were to turn that block on its end, now the area is very small, a mere 0.5 meters by 0.9 meters, or 0.45 meters squared. So if I want to calculate the pressure it's pushing down on the blue, it's going to be 45 newtons divided by 0.45 meters squared, or 100 newtons per meter squared. So even though we have the same object, the weight remains the same, the force remains the same, the pressure can be changed depending on how or where the contact is taking place. Now, I won't ask you on my test about pressure, force, and area. These will be questions that get asked when you take your physics class. But they have to do with matter and energy, and so I wanted you to understand that there are important considerations such as this. Now, I'll give you some examples. If I were to ask you which of these shoes would create the most pressure, you would say, well, the red high-heeled shoes probably, because there's a very small area that is holding all of the force of your body. These rather orthopedic looking shoes probably are going to be a little more comfortable as they spread the force out in a big area. Or you can use these old wooden tennis rackets. I think we call these things snowshoes. And they will put your force over a very large area so you don't sink into the snow. Alright, let's change gears a little bit. Let's kind of define some terms here. So it says, during a physical change, now I want to compare that to a chemical change, okay? So during a physical change, a substance changes some physical property. So what are we talking about? Well, in this picture I have here an iceberg, and that's made of water. The water that it's floating in is also made of water, and the sky with clouds is full of water as well. So I have water, but I have water in the solid, the liquid, and the gaseous state shown in that diagram. But it's still the same material with the same chemical composition. It all has the formula H2O. It doesn't matter if it's a solid, if it's a liquid, or if it's a gas. So if the material doesn't change, it has the same formula, that is a physical change or a state of matter change, not a chemical change. A chemical property, on the other hand, is going to change. So it says the tendency of a substance to change into another substance. In other words, at the end, when this chemical change has taken place, you do not have your original material. So here I have, it's hard to see, but this is a steel girder, maybe from holding up a bridge, and that's made of iron. But that iron is starting to rust. So you have iron reacting with oxygen, producing rust, Fe2O3. I wrote the balanced chemical equation down here for you again. At this point in your chemistry career, you don't need to write that formula down. You don't need to know it. But if you look at it, you can see what I start with, Fe and O2, is different than what I end up with, Fe2O3. Now they do have the same number of atoms, 4 atoms of iron on the reactant side. This 2 in front means I have 2 of everything here. That subscript 2 means 2 irons, but I have 2 groupings, so 4. I've got 3 groupings of O2. 3 times 2 is 6. 2 times 3 oxygen is also 6. So I've merely rearranged the atoms. That's what happens in a chemical reaction. That's what happens when a chemical property is observed. The atoms get rearranged, and the properties of what is formed is different than what you started with. So a chemical change is, again, involving the rearrangement of atoms into new combinations. A chemical reaction, then, is a chemical change. So it's the process of a chemical change. During a chemical reaction, new materials are formed by the way the atoms are bonded together in those new combinations. Now let's talk about the difference between what are physical properties and what are chemical properties. So I made a list. This is by no means an exhaustive list, but it's a rather good list. Physical properties can be observed without changing the substance. I can find out the boiling point of water by heating it up, and I'll still have water. I can freeze water, liquid water, into solid ice, and I still have water. So again, I'm not changing the substance. Now, luster might be a new term for you. It has to do with the shininess of metals. Metals are all shiny. We'll talk about the reason for that from a chemical sense in another lesson in a few days. But you can tell if something's shiny or not without doing a chemical reaction. Volatility means it evaporates easily, but it's just simply changing from a liquid to a gas, but it's still the same substance. You can tell if something's red or blue or colorless without changing it. You can taste it without changing it. You can use the Mohs scale of hardness to see if it's soft and can be compressed easy, or if it's hard like a diamond. Slipperiness is another property, a physical property. Bases, like bar of soap, if you wash your hands, very slippery. That's a physical property of a base. You can tell if something has an odor or not, again, without changing the substance. Ductility and malleability might be the first two new ones on this list. Ductility means a metal can be heated up and can be drawn into a thin wire without breaking. So if something can be heated up and drawn into a wire, it's ductile. Now, I think of the definition of, I use it as an example in my mind, duct tape. Duct tape has thin little pieces of metal embedded in that tape, and it's incredibly strong. And you can buy a spool of it. Well, you can also take a spool of wire and wind it up. So metals are ductile. Malleable means something can be hammered into shape without shattering. So maybe you've seen a coat of arms, like a metal medieval coat of arms that got pounded into the shape of a knight, right? Metal is malleable. You hit it with a hammer, it dents, but it doesn't shatter. Glass is non-malleable. You strike glass with a hammer and it shatters, but metals tend to be malleable. And again, I'm going to explain in this unit why metals are malleable, so you get a better understanding from the atomic level why metals are malleable. You can tell if something conducts an electric current without changing it. Metals tend to be conductors of electricity. Non-metals tend to be what we call insulators. Those are physical properties. Some substances dissolve in water, others do not. We'll learn about the polarity of a substance, and we'll learn a mantra or a saying that like dissolves like. Certain things like water will dissolve water-soluble substances, but oil and water do not mix. So if you were to try to take off a water-soluble substance from your skin with gasoline, it probably wouldn't work. Likewise, if you have oil on your skin, water will not take that off because they don't repel. But if you put a small amount of gasoline on a rag and rubbed off that material, it would come right off, although I wouldn't recommend using gasoline to clean yourself. You could also use a small amount of butter. Butter is what's called a non-polar substance. It's oily. It doesn't mix with water. So if I was doing some car repair and I got automotive grease all over my hands, I could use expensive soap and lots of soap to get it off, or I could simply take a small amount of cooking oil, maybe a spoonful of cooking oil. Then I could rub that in my hands and all the oil would dissolve, the grease would dissolve in the oil. I could take a paper towel and I could wipe off the grease from my hands that way. So a knowledge of these things is somewhat useful in an everyday sense. Viscosity has to do with the thickness or resistance to flow. Sometimes in the wintertime you'll get a runny nose and your nose just runs like water coming out of your nose. And other times that stuff, that mucus in your nose gets very viscous, very thick, and you can blow your nose all you want and see pretty yellow and green stuff coming out, right? But it's thick. Another spot where we might use the term viscosity is oil. Oil in older cars tends to be a thicker oil to coat the parts, but on newer automobiles it's much runnier, less viscous, because the parts have better tolerances and they're close together and they don't grind as much. All right, and finally, density. You can measure the density of a substance without changing it, and we'll do that. Density has to do with the ratio of mass to volume, and we'll spend a whole day talking about density. All of those properties can be measured without doing a chemical reaction. Or in other words, after you get the measurement, your original substance is still there. These are all examples of chemical properties. The only way a chemical property can be observed is if a chemical reaction occurs. And once that happens, you no longer have your original substance. If you burn something like magnesium or paper, you no longer have your original substance. It's gone. It's been burned up. Same when something explodes. Exploding is just deflagration or burning at a very rapid pace. When something tarnishes or oxidizes, it's corroding very slowly, so that iron rusting is actually a tarnish, right? Or maybe you have silverware that it's real silver coated and it turns black over time. Then you have to clean it because there's a chemical reaction that has taken place. Some things will react with acids and dissolve, or react with metals, or react with water, or react with nonmetals. Anytime there is a chemical reaction, that is a chemical property, and you will have new substances produced. All right. The bottom line here is chemical properties can only be observed during a chemical reaction. The atoms are rearranged and you no longer have your original starting material. So let's use some more vocabulary terms here. I'm going to use the term compound and mixture. Now these don't mean the same thing. So let's talk about the formation of a compound and the formation of a mixture. The formation of a compound means the atoms are rearranged into new combinations, and here's the kicker, they're chemically bonded together. So there's a chemical change. The formation of a mixture, the substances are next to one another, but they are retaining their original properties because they're not chemically bonding to one another, so that's a physical change. Let me say this another way. If you were to combine hydrogen and oxygen in the correct ratio and make a spark, they will form water, and they will no longer be flammable. That is a chemical change. If, though, you take sugar and dissolve it in water, or take salt and dissolve it in water, that's a mixture, and that is a physical change. Here's another difference. A compound has only a single correct ratio. Once it's formed, it will always be the same ratio. Water is always H2O. It's never HO2 or H3O or anything else. So compounds have a fixed composition, where mixtures can have a variable composition. You can have, maybe you're gargling, you have a sore throat, and you take some warm water and you can put 1 spoonful of salt in the water to gargle and it'll be salty, or you could put 3 spoonfuls of salt in the water and it'll be disgustingly salty, but all the salt will still dissolve. So mixtures can have a variable composition, compounds have a fixed composition. Okay? So that is a pretty big difference between a compound and a mixture. So let's look at this example here. I have a chunk of limestone. Chemically, it is calcium carbonate. That's what limestone is. If you compress that under lots and lots of pressure, that's what your marble countertop is, if you have marble countertops at home. And if you have marble countertops at home, you probably want to seal them. If you don't, if you get acid like lemon juice on there for too long, you can actually pit or corrode that marble surface. Even though it seems so hard and so everlasting, it can be damaged. If I take that chunk of limestone and I crush it in maybe a mortar and pestle and grind it up into a dust powder, that is simply a physical change because I still have calcium carbonate, just in smaller pieces. So there's my calcium carbonate or crushed limestone. A use for crushed limestone is to put in factories that are still using coal to burn. Coal, when it burns, produces sulfur dioxide and other gases that produce acid rain. And crushed limestone will absorb that sulfur dioxide. It's called a chemical scrubber, and it's how we can still use coal to burn for energy and maybe not pollute the environment quite as much. Now, if you heat up crushed limestone, what's going to happen? Let me light my match here. Pfft, there we go. Now it's going. Notice as I heat that, look at what happens next. I start to see this stuff decompose, and it generates some carbon dioxide gas. And when I'm all done, there's no more carbon dioxide gas coming off. Instead, there's just a residue of calcium oxide. So calcium carbonate decomposed, that is, atoms rearranged into new combinations, and made CaO and CO2. So this is a chemical change at this point. Notice that if I were to write that as an equation, I didn't, but I should have. I should have put an arrow going to it. On the reactant side, we have 1 calcium. On the product side, 1 calcium. On the reactant side, 1 carbon. On the product side, 1 carbon. On the reactant side, 3 oxygens. And on the product side, 2 oxygens here and another 1 here. So that's 3 oxygens there as well. So the same substance can undergo both a physical change or a chemical change. It's not like specific to a substance. Let's do another example. Many of you might have a bottle of hydrogen peroxide at your house, and it's probably stored in a medicine cabinet in a brown bottle. It has several uses. One use is you might use as an antiseptic. So maybe you are riding your skateboard and you fall over and you get like gravel and a little cut on your knee. Well, you can pour the hydrogen peroxide on there and it will bubble, and that's oxygen going to help clean out the little wound there. You can gargle with it if you don't want to use mouthwash. High amounts of oxygen will kill bacteria, although that's not what most people do with hydrogen peroxide, I suppose. You can dye your hair with it, I suppose. There's many uses. Why must it be stored in a brown bottle? Well, it says here that light hastens or speeds up the decomposition of hydrogen peroxide. So if I were to pour fresh hydrogen peroxide into the bottle and then put it in bright sunlight, what's going to happen is a chemical change. So the sunlight hits the hydrogen peroxide, and then what happens is the hydrogen peroxide decomposes by releasing oxygen, and the only thing you have left with is water. Now, there is an expiration date on the hydrogen peroxide. It might say best if used by December 2015. Well, what you have there is a bottle of water, no longer hydrogen peroxide. It has already decomposed. That's why they put the expiration date on there. So I said light will speed up the decomposition, but it'll break down even without being exposed to light because it's more stable as water than it is as hydrogen peroxide. So hopefully you recognize, even though this might look the same, they're both clear liquids, hydrogen peroxide and water, this is a chemical change because we have a new combination of atoms. All right, I'm going to stop there for right now. We will discuss types of bonds in our next lesson. Thanks for joining me. Thanks for sticking around. Bye-bye.